Our last main topic for today is to introduce using probability in actuarial science with what are called survival type random variables, sometimes also called lifetime random variables. These are random variables that conceivably could represent the lifetime of something. How long does a person live? How long does an animal live? How long does a dishwasher live? Live in quotes, right? Before it dies, before it breaks. Refrigerator, lawnmower, appliances are another common application of this kind of thing. Let T be the amount of time a person has left to live. Oh, sorry to be so blunt. Or how long any particular object will last until failure is a more general application. Then T is a continuous random variable, because we're talking time here, and amount of time that you could measure with arbitrary precision to the nearest year, nearest month, nearest week, nearest day, nearest hour, nearest minute, nearest second, nearest millisecond. Best to treat it as continuous. But it only takes on non-negative values. You can't say that something lives for -2 months. There's no probability of living -2 months or even less than -2 months. T has to be positive, or at least non-negative. Maybe you could say something dies right away, so it lives 0 months, but well, okay. Don't worry too much about that. We're trying to think about what we've been doing with random variables in this new context and come up with new ways of thinking about it that are commonly used in actuarial science. Here's the first new idea. Given a CDF for capital T, cumulative distribution function, capital F of T, our old friend, right? That's the probability that capital T is less than or equal to little t. Right? That's a CDF always. The corresponding survival function is just its complement. 1 minus capital F of T. It's the probability that capital T is, well, you could use a strict greater than here, or a greater than or equal to, because it's a continuous random variable, it doesn't matter. I'm using a sigma of T here for the name of the survival function. I should let you know that other books use an S. S for survival. Probably S is better. I'm going off of another book here that I haven't used in a while. Probably S is better because this sigma makes you think it's a standard deviation or something, but it's not. Okay, it's not a standard deviation. T does have a standard deviation, but it's not this function. This is a function called a survival function. It's just the complement of the CDF, 1 minus the CDF. As an integral, it's an integral not from 0 to t, but an integral from t to infinity. Why are we doing this? Well, it's not that we have to do it. One reason you might argue for talking about a survival function is just a more positive way of thinking about things. In fact, the entire field of actuarial science in the past, 50 to 100 years, has switched their point of view. And instead of using words like mortality, which is synonymous with death, they use words like survival. The CDF would represent the probability that you live less than t years, that you die before you reach age little t. But the survival function would be the probability that you survive until at least little t, right? Think of little t as a specific number like 50 or something. This is the probability that a newborn baby, say, lives at least 50 years. Hey, it's a positive way of thinking about it. Makes us happy. That's one reason for talking about the survival function instead of the CDF. Another reason is, you might say, more practical. In the context of a survival type random variable, the formulas for example, the mean, become simpler if you use the survival function. And the calculations become simpler, actually. And you can use the survival function in the way I'm going to show you here. Note that the derivative of the survival function, since the survival function is 1 minus the CDF, is in fact the opposite of the derivative of the CDF, meaning it's the opposite of the PDF. Meaning its derivative is never positive. It's always less than or equal to 0 because, right, PDFs are never negative, so their opposites are never positive. What is this? What's going on here? Let's think about it graphically. Show both here. What typically happens with survival type random variables, say an arbitrary survival type random variable, is the CDF, capital F of t, typically has a graph that, well, it is 0 when little t is negative, then becomes positive when little t is positive, and it increases. Technically speaking, CDFs can be constant for a while, like they are over here, like this one is over here. Even when t is positive, it could be constant for a while, though in practice that hardly ever happens. Maybe it increases, maybe it wobbles a little bit as it increases, let's say, but it approaches what as t goes to infinity? What's a horizontal asymptote here? 1. And maybe from a practical standpoint, it does have to effectively equal 1 at some point, right? Nobody lives past 120 years or so. So that's a general form of the CDF. It's the CDF. What's the survival function look like? The SF, I'll make that in red. It's 1 minus the CDF. So it's up at 1 when t is negative. And then it decreases, has a negative derivative when t is positive. And it is the complement of this. If 1/2 is, say, went right there, they got to cross at 1/2. Get some wobbles in there. That's the survival function, SF. Its derivative is always less than or equal to 0. It's either constant sometimes or in general decreasing. But that makes intuitive sense if you think about probabilities as well. The probability that you're going to live at least 70 years is less than the probability that you're going to live at least 50 years. 70 is bigger than 50. This function's decreasing. Here are a couple examples that are commonly used, though they're not super accurate for lives of people, at least over the long term. Exponential and uniform. Just as an example, suppose t is an exponential random variable with parameter beta equals 75. Remember, beta is the mean of an exponential random variable. So we'd be talking about, if we're talking about people here, we're saying we're trying to use an exponential distribution to model lifetimes of newborn babies. And we're saying they live on average 75 years. Now, 75 might be close to the average. I think it's a little higher, though it's gone down recently because of more drug use. That might be truly close to the average length of time to expect a baby to live. However, I will tell you an exponential distribution is not a very accurate distribution. It's not a good model. Let's just see what happens with it anyways. As far as the lambda goes, the lambda would be 1/75. Don't worry about the underlying Poisson process. Let's not talk about that. And t is a continuous survival random variable with SF, survival function, given by, what would it be? It's the complement of the CDF. You remember what the CDF is for an exponential? Probably don't. I actually did do an example with it, I think on Tuesday. It's 1 minus e to the negative lambda x. Alternatively, 1 minus e to the negative x over beta. The survival function is 1 minus that. So the 1 and the minus sign go away. It's just e to the negative t over beta here. E to the negative t over 75. I wrote it as an improper integral. But if you already knew what the CDF was, you wouldn't have to do the integral. Is that big enough? Can you see that? Back. Think about doing that integral. So what are we doing here? This is the PDF, right? Little f is the PDF. The PDF of an exponential is 1 over beta times e to the negative t over beta in this case. Beta is 75. If you integrate this, find an antiderivative of that, the 1 over 75 goes away and a negative sign is there. You could always double check this in your mind by differentiating. Differentiate this back this way. And you get this. I am playing around with slightly different letters here. This, you can see in this integral here that that's not a t, that's a tau. I could have used xi if I wanted to, right? Like I did before. Tau is a Greek letter. It's sort of a fancy looking t. Just trying to emphasize the true variable for the survival function is the lower limit of the integral here. It's not the dummy variable for the integrand function. You can call that whatever you want. Tau, xi, u, w, whatever you want. Technically speaking, improper integrals like this are limits, but we get a little sloppy here. When you plug in tau equals infinity, you got e to the negative infinity, which is not really a number, but we say it's 0 anyway. We get 0 minus this thing when we replace tau with t, which and the minus signs cancel. And you get e to the negative t over 75. That's the survival function. Yeah, that's an exponential decay. That's 1 when t is 0, as it has to be for a survival function. So the PDF is an exponential decay, and so is the survival function. It's not a coincidence here. But the PDF, this one has a vertical intercept at 1/75. It's lower, and it has, yeah, it's lower. The survival function starts up at 1. As another example, the computer survival function, suppose t has a uniform distribution. We actually haven't talked about uniform distributions much. I think I alluded to them in the table. What does this mean? Over the interval from 0 to 100. This means that the PDF of t is a constant function, horizontal line, over the given domain, 0 to 100 in this case. And it's 0 otherwise. If t is uniform on the interval from 0 to 100, I'm putting the extra square brackets in there. It's not traditional to do so. It really doesn't matter if you include the endpoints or not, right? Because it's a continuous random variable. So the PDF has a graph that's a horizontal line like that from 0 to 100. 0 otherwise. And again, it doesn't really matter whether you include these points as part of the graph or not, but I am. If that's going to be a PDF, what does the value on the vertical axis there have to be? If this is going to be a PDF, probability density function. Go ahead. 1/100th. 0.01, because it's got to integrate to 1. It's got to be a PDF. It's uniform, horizontal line. For any given interval of a fixed length, like a length of 1, the probability that the variable is in that interval is the same. Like the probability that t is between 10 and 11 is the same as the probability that it's between 27 and 28 is the same as the probability that's between 53 and 54. Because the area is always going to be the same, because the graph is a horizontal line. That's a uniform. So it's PDF. PDF you could write as being, well, if you wanted to write it as piecewise, you could say it's 0.01 if t is between 0 and 100, and you could say it's 0 otherwise. And the CDF is the integral of the PDF from minus infinity to t. I'll use a tau here, f of tau d tau, which, since this starts out having its first positive value at 0, is the same as the integral from 0 to t of 0.01 d tau. And that's going to be 0.01 tau evaluated from 0 to t, which will be 0.01 t. That's the CDF. So what's the survival function? Sigma of t. That's 1 minus the CDF. 1 minus 0.01 t. Technically, in writing this, I am assuming t is between 0 and 100. If t is between 0 and 100. And same thing here. If t is between 0 and 100. If you graph the survival function, it is technically 1 when t is negative. Its graph is a straight line with a vertical intercept of 1 and a slope of negative 0.01, and its t-intercept is going to be 100. It'll look like that. And then it'll be 0 after that point. That's sigma of t. For this model. And that's what I've got here, except I used fractions. It's equal to 1 when t is negative, and it's equal to 0 when t is bigger than 100 as well. I could write it in a piecewise way. Neither of these distributions is accurate for survival of people. Is one of them more accurate than the other? If I had to use one, which one would I use? I'd probably use a uniform. The exponential is way inaccurate for survival of people over long periods of time. It might be somewhat accurate for old people over short periods of time, but definitely not accurate for newborn babies. Another new concept called the force of mortality. Oh, we're not avoiding the word mortality here, and there's really no way to avoid it. In the book, this is called the hazard rate function. Actually, the content that we're talking about here is in the book, but with different symbols and with different terminology. It's the section about reliability near the end of chapter 4. You haven't read it. I haven't told you to read it. Section 4.7, it's titled The Weibull Distribution and Reliability is related to what we're talking about here. What's a force of mortality? It's another kind of function that can be computed from the survival function in a fairly simple way. Given a survival random variable, RV means random variable, with corresponding SF, survival function, the force of mortality, which is a function, is defined by this equation. Mu of t equals negative sigma prime of t divided by sigma of t. And the notation mu of t is pretty standard. But it's not a mean. So it's unfortunate that we're using sigma and mu in these contexts to stand for survival function and force of mortality, when sigma and mu in statistics also mean standard deviation and mean. Just realize these things are not standard deviations or means, though you can compute standard deviations and means using them. Maybe if we're after the standard deviation or mean of the random variable t, we should definitely use the subscript sigma sub t and mu sub t to emphasize that we're after the standard deviation and mean of a random variable. Yeah, we should do that. So mu of t is negative sigma prime of t divided by sigma of t. Remember, sigma of t itself is not negative, but it is in general decreasing. Sigma prime is never positive. By putting the negative sign in front of this thing, you are creating something that's never negative, typically positive. Could be zero sometimes. And what is it representing? It measures the instantaneous relative rate of decay of the survival function. To be official about it. Why? And what does that mean? Instantaneous rate of change is a derivative, right? The derivative tells you the instantaneous rate of change of a function, the slope of a tangent line. If I was after the instantaneous rate of decay for a decreasing function, I'd put a negative sign in front of that derivative because I'm using the word decay instead of change. I'm saying, hey, this function goes down, it's decaying. How fast is it decaying? I could give a description of that decay as a positive quantity, but because I'm using the word decay, that is emphasizing it's decreasing. So a negative derivative is a rate of decay for a function that decreases. Relative rate of decay is like a percent rate of decay. And how do you compute the percent change of something? Like if your bank account goes from $1,000 up to $1,100, the change has been 100 from 1,000 to 1,100. The percent change has been 10%. You took that change of $100 and divide by the starting amount of 1,000. 100 divided by 1,000 is 0.1, 10%. That's the idea of dividing by the derivative, or the function itself here. Is to convert this to a relative or percent rate of decay. The fact that we use the word decay is why the negative sign there ultimately gives us a positive quantity here. It can be interpreted in another way, but we probably should say a few more things first. And think about examples here. What is the force of mortality for an exponential random variable in a uniform? Let's do it by hand here. So for an exponential example, with mean beta, parameter beta, let's write down what we know. We know the PDF is 1 over beta e to the negative t over beta when t is greater than or equal to 0. We know the CDF, capital F of t, is 1 minus e to the negative t over beta when t is greater than or equal to 0. We know the survival function, sigma of t, is 1 minus that, which is this. We talked about this a few minutes ago when beta was 75. So what's the force of mortality? Mu of t, negative sigma prime of t divided by sigma of t. Negative, I've got to take the derivative of sigma of t. Already know it's negative f of t, actually. Negative 1 over beta, e to the negative t over beta. That gets divided by sigma of t itself. The e to the negative t over beta is divide out. The negative signs cancel. I'm left with the constant function 1 over beta, at least when t is greater than or equal to 0. For a exponential random variable, the force of mortality is constant. The PDF has a graph that is an exponential decay, vertical intercept at 1 over beta there. That's the graph of the PDF. Its relative rate of decay is constant. Percent rate of decay is constant. You've known that since calculus, maybe even pre-calculus. For exponential growth, the percent rate of growth is constant. For exponential decay, the percent rate of decay is constant. This is something you actually already know, just thinking about it in a new way. It's not a line, it's a curve. So its actual derivative, its actual rate of decay is not constant, but the relative rate of decay as a percent per unit time is constant. For any point, the slope of the tangent divided by the height of the graph is constant. So that's what the force of mortality is for exponential. What is the force of mortality for uniform? F of t is what? Well, we did the constant function 1 over 100 in the previous example. In actuarial science books, this is typically written as 1 over omega for t between 0 and omega, and 0 otherwise. I call omega the drop dead date, right? Under this model, nobody lives past omega years. That's your drop dead date. You're 1 minute before your drop dead date. Oh, sorry, I'm going to die in the next minute. It's only a model, okay? You don't take it too seriously. The CDF is going to be, well, technically 0 if t is negative, 1 if t is bigger than omega, and the integral of this, t over omega plus c, but the c will be 0 if t is between 0 and omega. That's the CDF. The survival function is the complement of that. 1 if t is negative, 0 if t is bigger than omega, and 1 minus this, 1 minus t over omega if t is between 0 and omega. That's a 1 minus t over omega if you can't quite tell. That's not a w, it's an omega. That's why mathematicians always make their w's pointy, because that's a w. This is not a w, it's an omega. It's like the z's and 2's like we talked about the other day. So now what is the force of mortality? Once again, it's negative sigma prime of t divided by sigma of t. Again, sigma prime really is the opposite of the PDF. So at least when t is between 0 and omega, let's say, we get the opposite of 1 over omega there. I differentiated this. Let's assume t is between 0 and omega here. I'm actually not going to assume it's one of the endpoints. I could assume it's, well, okay, yeah. Sigma is not differentiable at 0 or omega. Divided by sigma, divided by this thing, and you get this. The negative signs cancel. I can also multiply the top and the bottom by omega and get some cancellation, and I get this. That's not a constant function. It's a function whose graph looks like this. When t is 0, it's 1 over omega, which if omega, for example, is 100, would be 1 over 100. When t approaches omega, Graph's got a vertical asymptote there. Actually, back up here, I was just realizing, I graphed the PDF and I said it's got a constant relative rate of decay. But 1 over beta is not what that constant relative rate of decay is, because mu is measuring the constant relative rate of decay of the survival function, not the PDF. But the survival function is exponential decay as well. The force of mortality goes to infinity as t approaches omega. What does the graph of the survival function look like? Looks like this. It's got a constant rate of decay, but not a constant relative rate of decay. The relative rate of decay increases. What's going on? The slope is constant, but when you compute the relative rate of decay, you're dividing by smaller and smaller numbers. The height of the graph is getting lower and lower. And that's enough to make this ratio go off to infinity. In a practical standpoint, what does that mean? It means if this model were accurate and there's a drop dead date, and you're 1 minute from it, the fact that this graph is so high means you are almost guaranteed to die in the next 30 seconds and for sure guaranteed to die in the next minute. Okay? The force of mortality can be interpreted, if you're careful, as being proportional to dying in the next minute, say, or maybe even next day or week. Or if you don't want to think about people dying, think about appliances. Okay, going kaput. It is effectively proportional to the probability of dying in a small time interval. So the higher it is, the more likely you are going to die in the next time interval. Even that's not completely accurate, but it's almost accurate. Okay, so I won't go into details. Got 5 minutes. In 5 minutes, what is worth emphasizing here? Some calculations you're still going to need to be able to do. What do we always do with random variables? We compute their moments and their variances and standard deviations. The first moment, the mean of a survival type random variable, is the same formula as always. Integrate t times the PDF, but amazingly, ... you can show that that's the same as the integral of the survival function. Amazingly. This only works for survival random variables. It doesn't work, for example, for normal random variables that can take on negative values. This is a fact you can take to the bank and use on the homework. Got a name. The name is awesome, but I don't know where it came from. It's called the Darth Vader Rule. Why? I have no idea. But if you look up the Darth Vader Rule, actuarial science, you'll find this formula. Okay? The Darth Vader Rule. And that integral on the right, integrating the survival function, is typically easier than integrating the definition of the mean. Oftentimes, with the one on the left, you might have to use integration by parts, and the one on the right, you don't. In fact, to prove this, you can use integration by parts to prove it. The second moment has something similar happen. You don't have to integrate t squared times the PDF. Instead, you can integrate 2t times the survival function. You still have to use integration by parts typically, but at least it's just one integration by parts instead of two. Darth Vader Rule. Of course, don't forget, the second moment is not the same as the variance. If I ask you for the variance, You got to do the second moment minus the square of the first moment. It's always, yeah, even I forget that sometimes. Just like so excited to get the second moment that I think it's the variance. No, you're not done when you find the second moment. One last slide. It's the idea of something called a Curtate survival type random variable. Oh, 2 minutes for this. Where when you're thinking about how long somebody lives, you talk to your friend and they say, oh, my grandma died last week. And you ask how old were they? And they say, oh, they were 87. Well, really, were they really exactly 87? No, right? They're probably 87.639654321. But we say 87. We rounded their age down because that was their last birthday. That's what a Curtate survival random variable is about. Given a continuous survival random variable T, the Curtate future lifetime K is the greatest integer in T. So creating a new random variable from the original random variable, very much related to the original, take the age that they lived to and then round down to the nearest whole number. That's what this means. There's 2 slides left, but I think we only have time for this one slide. What's the P? Well, I probably should call this a PMF. What's the PMF of this? Probability mass function. Given a non-negative integer K, K could be 0. The probability that capital K equals little k by the complement rule, ultimately, actually the axiom 3 for mutually exclusive events, can be found like you see it here. And notice what you're doing is you are finding sigma of k minus sigma of k plus 1, where sigma is the survival function. Here are the formulas for the moments. They involve summations. Okay. Now we're about out of time, so I'm not explaining this. This is going to kind of seem mysterious in looking at all these equations. I could take 5-10 minutes to explain it more. It is stuff, in fact, you could figure out if you think about it hard enough. It's related to our rules for probability, and it's related to means and variances, second moments of discrete random variables. K is discrete, right? K is only going to take on whole number values starting at 0. I think there's one more slide that also gets into what's called, well, gets into conditional probabilities. We don't have time for that. Okay. That's a quick summary. Introducing the use of probability in actuarial science, mostly related to life insurance and also you could say warranties of cars and appliances. Okay. All right. Have a good day.